Hello, this is FlippedHarber for Physics, and in this video we'll go over the practice problems on page 128, number 17 through 21. In number 17, a girl exerts a 36 Newton horizontal force as she pulls a 52 Newton sled across a cement sidewalk at a constant speed. What is the coefficient of kinetic friction between the sidewalk and the metal sled runners? Ignore air resistance. So here we see a free body diagram for the four major forces acting on this sled. The normal force, the weight, the kinetic friction that we're trying to find, and the 36 Newton force that's pulling the sled along. Now, it's labeled as a 52 Newton sled, so they're actually telling me the weight of the sled. I don't want to multiply that by 9.80. That's the weight. That's mg. So, I'm going to go ahead and do a sum of forces in both the x direction. So that's got the 36 Newton force to the right, so that's positive, minus kinetic friction. It shows that my kinetic friction is equal to 36 newtons. Not a big surprise. And I'm going to do a sum of forces in the y direction, where we have the normal force minus the weight of the sled, the 52 newtons. Again, this shows that the normal force is equal to 52 newtons. Not a big surprise. Now, in both of these sum of forces, they were set equal to 0 because all sum of forces equal mass times acceleration. And as you can see labeled in the picture, acceleration is 0. That's because of the two words constant speed. Now, we go ahead and use our equation for kinetic friction. Kinetic friction is equal to mu, that is the coefficient of kinetic friction, times the normal force. So solving for mu, we get F sub k, that is the force from kinetic friction, divided by the normal force. Plugging in, we find out that the mu, the coefficient of kinetic friction, is equal to 0.69. Now, since this is a coefficient of friction, there's no units to this number. It's just plain old 0.69. Okay, let's move along. In number 18, you need to move a 105 kilogram sofa. Now, this time, they're telling us the mass of the sofa rather than the weight. So I'm going to need to change that to a weight. We're trying to move it to a different location in a room. It takes a force of 102 newtons to start it moving. What is the coefficient of static friction between the sofa and the carpet? So again, we'll start with the free body diagram with the four major forces drawn in. We know that the normal force has to equal the weight, so the normal force has to equal 1,029 newtons. The way I got that 1,029 newtons is I took the 105 kilogram of the sofa and multiplied by 9.80. The static friction has to be equal to the 102 newtons that it took to get it to start moving. So we just overcame static friction with a force of 102 newtons. Again, we'll use an equation for friction, but this time it's static friction. So it's mu sub s rather than mu sub k. And our coefficient of static friction is equal to our static frictional force divided by normal force. We plug in our numbers and we see that the mu sub k, that is the coefficient of, that's supposed to be mu sub s, the coefficient of static friction, is 0.0991. Now that's a pretty small coefficient of friction, probably because it's being pushed around on something like carpet where it can slide easily. Alright, Mr. Ames is dragging a box full of books from his office to his car. The box and books together have a combined weight of 134 newtons. Now they're telling us the weight. Don't multiply that by 9.80. If the coefficient of static friction between the pavement and the box is 0.55, how hard must Mr. Ames push the box in order to start it moving? So again, we'll start with a free body diagram, and we have to figure out how hard Mr. Ames has to push on this box. We know that the static friction is what we have to overcome, so our force is going to have to just equal static friction. Static friction is equal to mu times the normal force, and we'll just plug in 0.55 times 134 newtons, and we find out that the force that he needs to push with is 74 newtons. Alright, good luck, Mr. Ames. Alright, in number 20, suppose the sled from problem 17 is resting on packed snow. Now, anytime we change the surface, that's going to change the coefficient of friction. And it tells us that the coefficient of kinetic friction is now only 0.12, a much lower number. If a person weighing 650 newtons sits on the sled, what force is needed to pull the sled at a constant speed? Again, we'll do our free body diagram, but notice the changes. We don't know what the force is, we're trying to find it. And notice that our normal force, or excuse me, our weight is much bigger than it was before. We've got a 650 Newton person sitting on this sled that was already 52 newtons. So together they have a combined weight of 702 newtons. Now that's important. You've got to remember to add the weight of the person plus the weight of the sled. So the force that we need to pull with is equal to the kinetic friction. Take mu sub k times the normal force, and we find out that we need to pull with a force of 84 newtons in order to pull this sled at a constant speed. Now we would actually need to pull harder to get it to overcome the static friction, and then we could back it down to 84 newtons because this is the kinetic friction, and kinetic friction is always less than static friction. Alright, number 21. Suppose that a particular machine in a factory has two steel pieces that must rub against each other at a constant speed. Before either pieces has been treated to reduce friction, the force necessary to get them to perform properly is 5.8 newtons. After the pieces have been treated with oil, what will be the required force? So here we see our two pieces of steel, and we're going to need to figure out what this normal force is. It might not just be equal to the weight of the two pieces. There might be something that's pushing down on these pieces as they slide across. Now in order to accomplish that, we're actually going to plug in the 5.8 newtons that it takes to move the two pieces across each other, and we're going to look up the mu sub k for steel on steel when it's dry. Now that's equal to 0.58, and I got that from the table that shows us typical coefficients of friction. So we find out that the normal force on these two pieces of steel is 10 newtons. That may be less than or more than their weight. It just depends on what the machine is doing with these two pieces. But we know that the normal force is 10 newtons. Now we'll use that 10 newtons in order to find our new force when we use a much lower mu sub k, which is steel on steel with oil. So now our mu is only 0.06, much less than it was before. Doesn't sound like a big change, but notice that the force is now only 0.6 newtons. Okay, so it's time for you to try some on your own. I'll see you in class, and I'll see you online.